It's interesting to think about something you've worked on for 16 years and it's sitting on top of a rocket and now it's going to hurtle into space and you just hope it gets there. We have collaborators from France, Italy, Japan, Sweden, Germany, and of course the US. Because the light is so energetic, you cannot focus it like you would light with an optical telescope.
Overall, a gamma ray passing through the glass structure has about a 65% chance of becoming an electron-positron pair on its passage through this material.
So we'll see a particle and an antiparticle, matter and antimatter, materialize inside the detector, and then we can track the direction of the charged particles and, in a sense, take a photograph of the particles as they go through the detector. And by reconstructing the direction of the charged particles that are created, the two charged particles, we can trace them back, figure out where the pair conversion event occurred, where the gamma ray converted into the particles, and then point back and figure out where the gamma ray came from. And in that way, we effectively have a telescope, because we can trace back where the gamma ray came from on the sky. The shortest timescale sources we're going to see are what are called gamma ray bursts. And these occur in random directions on the sky about twice per day. And the duration of a gamma ray burst is anywhere from a few thousandths of a second to perhaps 100 or 1,000 seconds. And when the gamma ray burst is on, it is the brightest, most energetic source in the sky. So in that brief period of time, say 1 second, for example, the gamma ray burst will put out more energy in 1 second than the entire rest of the universe. So the source of these gamma ray bursts, we believe, are stellar explosions near the end points of the life of a massive star as it forms a black hole. That's one kind of source. The other favorite conjectured model for a gamma ray burst is the coalescence of two compact objects like neutron stars that are orbiting each other. And as they orbit each other, they lose energy due to the emission of gravitational radiation, and eventually they coalesce together. And at that moment they coalesce, there are predictions they will emit a burst of gamma rays. So in fact, we expect to observe that kind of phenomena as well. So in order to catch these things, we have to be looking in the right direction. So that's where the Large Area Telescope on the GLAST mission is very important. It has an enormous field of view. And so every orbit we go around the Earth, we survey the entire sky. So if a gamma ray burst goes off and we catch it in our field of view, we can in fact issue an alert autonomously to the spacecraft. And the spacecraft will then, instead of continuing to do this scanning survey of the entire sky, will interrupt the scan and point in the direction of the gamma ray burst. And that alert goes out across the world via the internet. All of the data from this observatory goes public, and any scientist anywhere in the world can access it and use it. I think the most exciting discoveries we're going to make with GLAST are probably the things we haven't thought of. But among the list of phenomena that we might see that we've actually thought about, the detection of dark matter would perhaps be the most exciting discovery. We know that it's out there in space because of its gravitational effects that we can observe. You know, the tug of the gravity of our galaxy on nearby satellite galaxies tells us there's more matter in our galaxy than can be accounted for with the matter that emits light that we see around us. So there's much more matter there. So one possibility is that GLAST will detect gamma rays from the annihilation that's predicted to occur when two dark matter particles meet each other. So one of the things GLAST will do is look for the gamma ray signatures of dark matter. And I have to say, That's a very difficult undertaking to sort those gamma rays out from the gamma rays generated by everything else. And we have some ideas how to do that. But I have to say, if we succeed, that would in fact be probably the most important discovery we would make.